Hello, good evening, everyone. Welcome to the next live session for the course Characterization of Construction Materials. So, in today's live session, we will be discussing the topics which were covered in the week 11, right? In week 11, we learned more about the NMR spectroscopy and we learned how to quantify and how to determine the porosity using mercury intrusion porosimetry. And these two new characterization techniques were discussed in detail in the previous week. So, like the previous sessions, in today's session also, I'll share the screen and I'll show the question on the screen. And please try to answer those using the chat box. So, try to make it interactive. Otherwise, it will be just a monologue from my end. So, let me try sharing the screen now. Please confirm if the screen is visible to you. Yeah. Is the screen visible? Can someone please confirm in the chat box? Yeah. Thank you. So, yeah, this is perfect. Fine. So, let's move to the first question. So, this question is related to the NMR. So, it is a true or false question. Okay. So, the question is a nucleus with odd atomic number or odd mass number has a nuclear spin. You have to state whether the statement is true or false. I guess there's a network issue from my end. Am I audible now? Sorry, there was a network connection problem from my end. So let me try to share it again. Yeah, I hope the screen is visible now. So the question which I was asking was a nucleus with an odd atomic number or odd mass number has a nuclear spin. State true or false. Okay. Yeah. What about others? So there are two responses that it is true. What about others? Mehna and Javed. Okay. So the correct answer is option A, that is true. A nucleus with an odd atomic number or an odd mass number has a nuclear spin, and it is based on this nuclear spin that we characterize a material through nuclear magnetic resonance or NMR. So let's move to the next question. The chemical shift in NMR spectroscopy is measured in dash. So, what is the unit of measurement of chemical shift in NMR spectroscopy? Is it in nanometer, millimeter, parts per million, or angstrom? The chemical shift in NMR spectroscopy is measured in dash. What is the unit of measurement of chemical shift in NMR spectroscopy? Any answer? Okay, Pratiksha goes with ppm. Nila also goes with ppm. Who else? What about others? Okay, there's a natural tendency to go for the answers which is in distance, like in a nanometer or length based units. But the correct answer is ppm. Okay, this is the term, or this is the equation for the chemical shift of nuclear magnetic resonance spectroscopy result. So this shift is measured in terms of ppm. Okay. Thanks for those who are responding in the chat box. Please continue to do the same. Okay. The next question is here. The reference material generally used in measuring the chemical shift in NMR is tetramethylsilane. The shift of this material is dash. Okay, so Pratiksha goes with option A, that is 0. So she says that the chemical shift of tetramethylsilane in NMR spectroscopy is 0. What about others? Anyone else? It's okay even if it is wrong. Okay, Smita goes with C, that is 1. Fine, let's move to the correct answer. The correct answer is option A, which is 0. So, here, if you see the snippet from the presentation, the reference is usually taken as TMS or tetramethylsilane. Why? Because it is unreactive with the sample. For any characterization technique, if you need to have a reference material, it has to be unreactive with the sample. So it is unreactive with the organic compounds, it is volatile and gives absorption which is mostly shielded. And here the chemical shift of reference, this chemical shift is given by this equation, that is delta is equal to nu of the, or the frequency of the sample minus nu of the reference by nu of the reference into 10 power 6. So here the reference is, when the reference is kept, then nu of sample is equal to the nu of reference. So as a result of which the delta becomes 0. So the numerator will become 0 because nu of sample is the same as nu of reference. So we get the delta as 0 in the case of tetramethylsilane. Let's try to look into the next one. Yeah. The intensity of shielding of nucleus by the electrons affect the chemical shift value. As the shielding intensity increases, what happens to the value or the chemical shift value? It becomes more positive or becomes more negative. What happens to the chemical shift when the shielding of nucleus by electrons increases? Okay, so I've received two responses. Let's look into the correct answer. Yeah, the correct answer is B. So as the shielding with the electrons increases, the chemical shift value becomes more negative. So in order to remember this concept, you can just think that electrons are having a negative sign or the negative potential. So more and more electrons shield our sample, then more negative the chemical shift value will be. So maybe you can correlate and you can remember this concept in such a way. So as the shielding with the electrons increases, the chemical shift value moves towards the negative, becomes more negative. Okay, moving to the next question. The octahedral alumina will have dash the tetrahedral alumina. Same shielding as the tetrahedral alumina or higher shielding than the tetrahedral alumina or lesser shielding than the tetrahedral alumina. So this is related to the coordination state of alumina. So what happens when it is octahedral alumina and tetrahedral alumina? Option A says that the shielding is the same. Option B says when it is octahedral, it has a higher shielding than compared to the tetrahedral. And option C says octahedral has a lesser shielding than the tetrahedral alumina. Okay, I received one response, that is C, lesser shielding. Let me wait for the other responses as well. Okay, I guess that's the only response I'm receiving. Correct answer is option B, that is higher shielding. So the in the region corresponding so here when the aluminium atoms are in coordination of 4, 5 and 6. So this is a tetrahedral alumina, this is a octahedral alumina. There is a more of a shielding. When it becomes octahedral alumina, there are 6, it is in a coordination number of 6, so it has 6 atoms around it. So when it becomes a tetrahedral alumina, it has only 4 atoms. So the shielding is much higher in the case of octahedral alumina and not in the case of tetrahedral alumina. So even if you see the picture, you can see that this particular violet atom is is less shielded than this particular atom. All the other atoms, pink atoms, are shielding this violet atom. So the amount of shielding or the extent of shielding is more in the case of, but this one particularly, that is octahedral, and not this one which is tetrahedral. So octahedral alumina will have a higher shielding than the tetrahedral alumina. Okay. So let's move to the next concept, that is regarding the pore size distribution and porosity measurement. Dash is a pore of diameter less than 2 nanometer. So if you have a pore and it has a size of say 1 nanometer, is it a micropore, mesopore, or macropore? When the size of the pore is less than 2 nanometer diameter, what is it known as? Is it a micropore, mesopore, or macropore? Okay, you've received one response. Smita says it's mesopore. Let's see what others think. What about others? Mehna, Javed, Pratiksha. Anyone else? Okay. The correct answer is option A, that is a micropore. So here, if it is less than 2 nanometer diameter, it is known as a micropore. And if it is between 2 nanometer and 50 nanometer, it is known as a mesopore. If it is greater than 50 nanometer, it is a macropore. So 2, between 2 and 50, greater than 2. Sorry, greater than 50. Less than 2 nanometer, between 2 nanometer and 50 nanometer, greater than 50 nanometer. This is the criteria. So if it is less than 2 nanometer, it is known as a micropore. Okay, let's move to the next one. So there are two statements, statements A and B. Statement A says that a void is a three-dimensional entity in the cementitious system with finite size. Now, the statement B says all the pores are voids, but all the voids are not pores. Choose the correct statement. A is correct, B is false. A is false, but B is correct. Both A and B are correct. Both A and B are false. Okay. I received one response with two responses. Okay. Let's move to the correct answer. Yeah. Okay. Correct answer is option C. So let's see the statement A. Obviously, a void is a 3D entity. A void means uh, it's an absence of any material. So it is a three-dimensional entity. It has a finite size. So the statement A is definitely true. Now, what about B? All pores are voids. That is very true. If there is a void, it is a pore also. But all the voids are not pores. So for a pore to exist, it has to have a definite length also. It has to extend. It has to be like a tunnel in a very macro scale. If you see a small pit and a tunnel, you can imagine like that. So all the pores are voids by definition, but all the voids just cannot be pores. For it to be a pore, for the void to be a pore, it has to have a definite length also. So both the statements are correct. So both A and B are correct. So the option C is the correct answer. Let's move to the next one. A gel pore in cementitious matrix is a pore having size less than 10 nanometer, greater than 10 nanometer, less than 100 micrometer, 100 micrometer to 1 millimeter. So, what is the size of the gel pore? Okay. Okay, let's see the correct answer. Correct answer is option A, that is less than 10 nanometer. That is the size of a gel pore. So gel pores are those pores which is within the CSH gel, which is a hydration product. So within that hydration product, the gel pores are present and the size is less than 10 nanometer. Let's move to the next one then. So here you have to calculate the apparent density and true density of a material. So the mass of the solid phase is 5 gram, volume of the solid phase is 1 centimeter cube, and volume of the pores within the material filled with air is zero point 0.1 centimeter cube. So what is the apparent density and true density? Calculate the apparent density and true density. The mass of the solid phase is 5. Volume of the solid phase is 1 centimeter cube. And volume of the pores which is filling the with air is zero point 0.1 centimeter cube. Okay, I received one response. What about others? Okay, I received only one response. What about others? So apparent density is what? Mass by volume. So mass is given as 5 gram. Now what volume will you take for apparent density? You should take the volume of the solid plus volume of the air also. So 5 by 1.1 will be the apparent density, whereas true density meaning mass of solids by volume of solids, that is 5 by 1. So thereby the correct answer is option A. 5 by 1.1 will be 4.54. 5 by 1 will be 5. So the correct answer is apparent density is 4.54 gram per cc and true density is 5 gram per cc, that is corresponding to option A. Please try to respond or please try to be engaging in the chat box. Yeah. Let's move to the next question now. Identify the type of pores given in the figure. So, this figure, there is this A, B, and C. So, what are the type of pores? Is A closed pore, B an open pore, C an ink bottle pore? Or A and B are open pores, whereas C is an ink bottle pore? Or A and B are closed pores and C an ink bottle pore? Or A is an open pore, B is a closed pore, C is an ink bottle pore? Okay, I received one response. Thank you for responding in the chat box. Okay, Pratiksha and Smita had also responded as D. Anyone else? Okay, the correct answer is option D. So here, if this is a material, as you can see, this particular pore opens to the outside, external atmosphere. So this is an open pore. Whereas this one, particularly this B1 and all the other which these are around it, these are confined within the material and this does not open to the external atmosphere. So these are closed pores. Whereas option C, it has a smaller opening, whereas it extends to a bigger volume. So that is known as an ink bottle, particularly because of its shape, which resembles the older ink bottles. So it has a opening which is narrow, and then it becomes a higher volume. It fills a higher volume. Okay, let's move to the next question. Yeah. Mercury intrusion porosimetry or MIP is a useful technique to determine the porosity. In MIP, the sample is impregnated with mercury, which adheres to the pore walls on the application of pressure. State true or false. It's a true or false question. The sample is impregnated with mercury in MIP, and then the mercury adheres to the pore walls on the application of pressure. Okay. So I've received a response. Pratiksha, Javed, and Smita goes with option A. That is true. Anyone else? Okay. Let's see the correct answer. The correct answer is false. Why? Because mercury is a non-wetting liquid. It does not adhere into the pore walls. It does not. It just simply fills the pores. It occupies the space wherever there is an open pore. That much is that. That's it. It does not adhere or it does not get attached into the pore walls. It does not get absorbs or absorbs into the pore walls of the material, even if we apply the pressure. So mercury is a non-wetting material in nature. So that is why this particular statement that the mercury adheres into the pore walls on application of pressure is a false statement. Let's move to the next one. Contact angle of a non-wetting liquid at a surface is right angle, acute angle, or obtuse angle. So, what is the contact angle of a non-wetting liquid at a surface? Anyone? Okay, let's see. The correct answer is option C, that is an obtuse angle. So, here if you see, any acute angle means the angle is less than 90 degree, where the nature of the liquid is wetting. For a material to be a non-wetting liquid, it has to be greater than 9. The contact angle has to be greater than 90 degree. That is an obtuse angle. So the correct answer is option C. Let's move to the next part. Yeah. Higher formation factor is an indication of higher durability. This is a straightforward question without much of a need for an explanation. What is a formation factor is a question for the assignment. So I'll just keep that out from today's discussion. So we just need to discuss for a system of higher durability, higher formation factor is desirable or not. Okay, the correct answer is true. So as higher the formation factor, higher will be the durability of the material. Let's move to the next question. So there are two statements again. Statement A says lime mortar has a more refined pore structure than cement mortars. Option B says CSH has better pore filling characteristics than calcium carbonate. Choose the correct statements. A is true and R is the correct reasoning for A. A and R are false. A is true but R is not the correct reasoning for A. A is false but R is true. So this is regarding the properties of lime mortar and cement mortar. So the option A says the more refined pores are seen in or pore structure is seen in lime mortar. Option B says CSH has a better pore filling characteristics than calcium carbonate. Anyone? Just try to understand the concept behind this and respond in the chat box. Okay, let's look into the answer. The correct answer is option D. So option D is A is false but R is true. So what is A? Lime mortar has a more refined pore structure, which is totally wrong. It has the cement mortar has a more refined pore structure. Lime mortar has more coarsened pores. Then B is true statement, and it clearly explains why A is false. So in the case of pure lime mortar, the product on hardening or setting is calcium carbonate. But more than calcium carbonate, calcium silicate hydrate, that is the hydration product in cement mortars, has a better pore filling characteristic. So CHS has a better pore filling characteristic than calcium carbonate. So option B is true. Because of that reason, cement mortars have a more refined pore structure compared to lime mortar. Okay, let's move to the next question. Crystallization pressure exerted on the walls of a larger pore is dash the pressure exerted on the walls of a smaller pore during salt crystallization. So, regarding the structures along the coastal area, and whenever there is an exposure to salt, the along with the moisture, the salt can get into the structure and crystallize within the structure. So when the salt crystallizes, a pressure is exerted on the walls. So suppose it is a larger pore, and if it is a normal pore, sorry, a smaller pore, the statement says that the crystallization pressure exerted on the larger pore is dash the pressure exerted on a smaller pore. Is it the same, or is it more, or is it less? Okay, let's move to the correct answer. The correct answer is option C, that is lesser. So, if it is a small pore, okay, suppose we have pore A and pore B. Pore A is a small pore, pore B is a very large pore. Then, if a salt crystallizes, it has all the space around it to crystallize in the case of a large pore, that is pore B. But in the case of pore A, it has only a very little space for it to crystallize. So it faces some restrictions from around. Something hinders the growth. So as a result, it exerts the pressure as it grows and as it crystallizes. So the pressure exerted on a smaller pore will be much higher because the restraint faced by the crystal within the small pore is much higher than the restraint faced by the crystal in a larger pore. In the larger pore, there's more space. It can grow wherever, in whichever direction it want. So the pressure will be lesser. Okay, let's move to the last question for today. The threshold pore size in an OPC with respect to curing period increases, decreases, or remains more or less the same. Okay. So the correct answer is option B, that is decreases. So if you know the concept of curing or the curing period, as the hydration increases or as the setting keeps on happening, the pores will be more and more refined. The threshold pore size is the maximum or the largest size which has to largest size of a pore which has to overcome when in order to fill the entire open pores in a material. So if you have a material, the largest size of a pore which has to be overcome to fill the entire open pores with the mercury in MIP is known as a threshold pore size. So if you see, this is the red line indicates the OPC for 3 days curing, orange is OPC for 7 days. So here is a threshold pore size. So this slanting line, the starting point, maybe you can see, you can consider as the threshold pore size. Actually we draw the tangents at both these locations and find the threshold. So suppose the threshold of the red line is here, threshold of orange line shifts to the left. Obviously it's very clear that the threshold of the light green line shift to the left again, and for the dark green also it shifts. So as the size shifts towards the left, the size or the pore size decreases. So the question is threshold pore size in an OPC with respect to curing period dash. So it obviously decreases. So yeah, let me stop sharing and let me save the recording.